In the previous two videos, I did a quick summary and overview of truth values. I also introduced the first 5 main truth tables that, all things considered, you're just going to need to know to memorize. In the event that you didn't look at any of those videos, I want to quickly summarize more or less what those truth tables are again here. And then I'm going to hop over and I'm going to start showing folks how to do more or less truth table tests on various well-formed formulas to figure out whether or not their tautology is contingent or inconsistent. In doing so, I'm also going to take the time to unpack a little bit more why it is that we use truth tables and why we use a specific pattern of T's and F's in that key column. But let's start by reviewing again the basic truth tables. So let's make some truth tables that we're going to use. That should be about good enough for what we're going to do. So let's start with a single atomic well-formed formula, given that that's what we're calling it, at least according to Lemon. And by that I mean, let's just say that we were given an A. If we were given an A, we note that there is only one letter on this side. And since there's one letter on that side, that means we only put one letter on this side, namely an A. Our pattern for single letter well-formed formulas is just one T and one F. Namely, A is either going to be true or A is going to be false. If A represents, say, the proposition that Sam has a penguin, that proposition is either true, that Sam has a penguin, or it's false. And then all we do is we take all the values over here and we more or less copy and paste them in order under whatever letter matches this letter. Oops, that's wrong. Whatever letter matches that letter. Now, if we have a negated letter, the negation modifies the A. Since we have one letter over here, we're going to have one letter over here, the A, write down a T, write down an F, and then again we bring these little letters over, T and F. Now let's review the more complex ones where we have two letters. Let's do and statements first. A and B. Since we have two letters over here, we need two over here. We put the A first and the B second, since that's the order that they are on this side. Then the order is two T's and two F's. And then alternate T's and F's for our base column. Then again, we bring these over under every letter that matches. Our main operator is a conjunction. Conjunctions are only true when both sides are true, which means that the only true part is this one. And the other three are false. Now let's do a disjunction, A or B. Again, we have two letters over here, which means we need two letters over here. A goes first, B goes second. We follow our pattern of T, T, F, F. Then we follow our pattern for the base column, which is alternating T's and F's. Bring everything over. And we identify our main operator. The main operator here is a wedge. For a wedge to be true, at least one of the pieces has to be true. So T or T is true, T or F is true, F or T is true, but F or F is false. Then let's do an arrow very quickly. A, arrow B, two letters, need two letters over here. Fill in with our pattern. Again, if instead of counting sheep, you start counting T's and F's, you're doing this too much. Then we bring these over. And we think about our pattern again. For arrows, the only place where an arrow is false if it's a T, arrow, F. Everywhere else is true. And last but not least, the biconditional. A, arrow, B. Since we have two letters on that side, two letters on this side, then we follow our pattern once more of two T's and two F's, and then alternating T's and F's in our base column. We bring those values over under the respective letters that match. And then we identify the main operator. In this case, the main operator is a biconditional, and biconditionals are true if and only if it's the case that the two letters match. So if you have two T's, it's true. If you have two F's, it's true. But if you have a T and an F, that's false. Think of this as a definitional type of thing, where definitions should actually be equivalent. So if what you're seeing is not equivalent, something has gone wrong somewhere. Now that we have these 6 truth tables in mind, it's really 5. This one is kind of just clarifying how negations work. We're going to be able to look at well-formed formulas and ask, hey, what kind of well-formed formula is it? And we're going to be given 3 different options. Namely, we're going to be given the option of it being a tautology, a contingency, or it's really a contradiction, but we're going to call it an inconsistency. A tautology means true. In this case, if we have under our main operator all T's, it's a tautology. Contingent means sometimes. And to translate that, that means that we have T's and F's. It doesn't actually tell us how many T's or how many F's we have, but if we have a mixture of both of them, then it's going to be contingent. And inconsistency means false. This means we have all F's. And inconsistency also means a contradiction. So it means that there's no possible state of the world, there's no possible combination of the different letters and the different truth values where anything would ever end up being true. So a quick example of this is A and not A. And I'll actually do this truth table first. This is going to be an inconsistency. There is no possible world on which or in which this would end up being true. So let's see. Let's draw a truth table for it. So this will be our first truth table that we're going to analyze. I'll start by drawing the truth table. Put our A and not A over here. A thing to note is that we only actually have one letter on this side, namely an A. Even though there are A and a not A, the base of both of those is just A, and that only counts for one letter. So we're only going to have one letter on this side. And we're just going to fill in the truth table like this. Then we bring these over and put them under the A's. So TF and go there, T and F and go here. Our main operator is going to be the and, but notice that the A on this side is being modified by this negation. So that means that we need to negate everything under this A. And in negating it, we flip the signs. That becomes an F, that becomes a T. And then when we go to analyze the main operator, what we find is T and F, well, that's false. Because for an and to be true, we need both of the sides to be true. And F and T, well, that's also false. Again, for an and statement to be true, it has to be the case that both of the pieces are true. If even one of the pieces is false, that can't be a true statement overall. And then, since we find that our main operator has all F's, this would mean that this is inconsistent. There's no possible world in which this could possibly be true. Let's run through a few more examples. And these are going to be straight from Lemon, but I'm just going to walk through a number of them, except your homework ones. So if you're watching this and at some point you get it, skip towards the end where I start unpacking again why it is that we use a specific pattern in our key, our key section of the truth table. But for now, let's just stick together and do a few of these. You did a few of these in class. I'm going to redo them. And I'm just going to draw a few. That way we can have these all ready. There we go. Let's start with P, arrow P. Like before, there's only one letter technically on this side. A P is a P no matter where it is. So we write P on this side. We follow our pattern of T and F since there's only one letter. Then we plug it in under the variables. T arrow T is true. F arrow F is true. And our main operator here was an arrow. Since we find all t's, this is a tautology. Now let's do p, arrow, not p. Again, we only have one letter to worry about, p. Fill it in, bring everything over. But notice that we have a negation here. That means that before we can fill in the main operator, which is the arrow, we need to flip all the signs on this side due to the negation. So that becomes an F, and that becomes a T. And then what we compare is we compare this column and this column. So in the event that you have something that looks like this, let's say a negation P or negation of A, arrow B, that's an arrow. As soon as you end up moving into this column, it's pretty much as if none of this ever happened. You're going to ignore all those columns and you're just going to continue to look at this column moving forward for the rest of the proof. We'll see that for some others later. For now, let's get back to this one. T arrow F is false. F arrow T, though, is true. Since we have a mixture of falses and true, this is contingent. Now let's look at not. P arrow P. Again, we only have one type of letter, a P. So we follow our pattern of writing a T and an F. We plug everything in under the letters. Then we ask, what's our main operator? In this case, the main operator is actually the negation out here. The negation is over the entire parentheses, which means we're going to want to figure out the parentheses first and then come back and do the negation. So let's work within the parentheses. T arrow T is true. F arrow F is true. And then now we can go out here to the negation column and we get to flip the sign of this column right here. So that becomes an F and that becomes an F. Since everything is now an F, this is a inconsistency. One of the questions that I saw a lot on homework exam or homework questions based on emails and then also in the participation pages was folks were asking which column. And by this, I mean which column do we look for when we're trying to negate things? And the answer is you ask which thing is the main operator within the parentheses. So let's pretend for a second that we didn't have this negation out here. What would the main operator be? Well, the arrow. As such, when we're trying to figure out what to do with the negation, we're going to figure out that main operator inside the parentheses first, and then we negate that column using the negation out here. Let's keep going. Let's do just P. This is easy. There's only one letter. Write down a T and an F. Write down T and an F here. In this case, we have like an implicit main operator of just the letter. And since we find T's and F's, this is contingent.